So in this research, we are going to discuss about how AI or the artificial intelligence and computer vision both can be used for autonomous vehicles, right? So nowadays, when we hear this term autonomous vehicles and self-driving car, there are so many things that are coming to our mind, because nowadays we see so many videos coming out, right, where a car is moving on its own, right? You must have seen some videos from Tesla, where Elon Musk, the CEO, you must have seen some videos where every now and then they come up with videos where the car is moving autonomously. Now the question is how that technology is done. How do we reach to a stage where a complete driver aided vehicle is converted to a driverless vehicle, right? There should be something, right? Let's say you are thinking about a human being. We are equipped with different sensors, biological sensor. We have our eyes, we have the touch sensor, we can move our head, right? We can feel our environment. Based on that, we take some decision how we will move. Let's say this is the room that I entered into. I don't know about this room before entering. But when I entered to this room, I scanned this room through my eyes. Then based on that, I found out, okay, this is what is the distance. These are the people who are here, right? Based on that, I created a map of this environment, right? And then I started moving, right? So this is what is happening in my brain. So there should be something for the car that should do the same thing, right? When we are moving in a car environment, there also when we are driving, we see what is coming to our left, what is coming to our right, we see our mirrors, what is happening in the back, what is happening in the front, and based on that we take those decisions. Now all these decisions needs to be taken by the car without the help of the driver. Understood? So there should be some computer system which should do that. Now to aid to that computer system, there should be some sensors connected, right? So that is where AI and computer vision will come into picture. How the data that is coming out of different sensors, I will discuss about different sensors, what can be connected, how the data coming out of all these sensors can be used through different AI and computer vision algorithms to process in such a way that the car will move autonomously, right? So this is the gist of this talk. So when it comes to a self-driving car, as I explained about, the car should move autonomously with the help of sensors. Again, there is not just only one car, there is a fleet of cars that should be on the road. Okay, it is not about just we are talking about only one car that will move autonomously, right? If just one car moves autonomously and others are driver cars, it will create a very difficult scenario, right? It can create very critical scenarios also. Okay, so it's all about where all the cars should move autonomously. And all the cars should be equipped with different sensors. At the same time, there should be some vehicular to vehicular communication, V2V communication that should also happen, so that they should know where the other vehicles are, right? So we are talking about an environment where all the cars should move autonomously on a road, right? Maybe it is not a reality now, but in future it is a reality, right? In India, it might take some time, even it can take up to 20 years. But in foreign environments, you must have seen in the controlled scenarios, they are able to run it. In controlled scenarios, not in like full highway traffic, but in controlled scenarios where they know how the traffic would move, and where they know that other vehicles, they are not going to create such difficult scenarios for them. Those scenarios, they are able to run it. That is where they are creating these videos. I think 2 days back, one video came where Baba Ramdev was driving in a self-driving car, and he created a video and posted it. So in foreign countries, they are able to do it. Okay, in India, we know the scenarios are very tough, right? Because we don't know anyone come from any side, right? So we need a controlled scenario first. Then from controlled scenarios, slowly we can move to very difficult scenarios like highway traffics and all. Okay. So if you come to the market, you see global autonomous vehicle market from 2029 to 2026, it is going to get, the market is going to grow at a rate of 557 billion. Okay, the cumulative average growth is 39.5%. Right, so many researchers and so many companies are nowadays working on it. Okay, in India also you will find many companies. I know one company known as Sweat Robotics. They have come up with their own vehicle which is moving very good. They showed some video where the vehicle was able to move near a these checkposts are there, right, on the roads, highway roads. There also it is able to move without any issues. Okay, so in India also this is like already many researchers are working on it. Also, if you read about the research papers, right, generally this autonomous vehicles or advanced driver assistance system, that term will be used. Okay, they will not use this term self-driving car. Self-driving car is like a layman term. Like if you tell to someone outside, they will understand it. But if you go to research papers and all, generally advanced driver assistance system. Okay, that is the term that is used. I'll tell you why it is known as advanced driver assistance system. Okay. Many companies, if you see, like General Motors, Daimler, Ford, you name any company nowadays, right? They have the research wing where they are working on self-driving cars. When I say any companies, means automobile companies, right? So they have their own research wing where this autonomous vehicle research they are doing it, right? So I will not go to all in details of all this. Okay. Now the question is why it is known as a advanced driver assistance system. Okay. So the Society of Automated Engineers, this SAE, they have defined different levels of autonomy, starting from level 0 to level 5. Okay. So starting from level 0 to level 5, they have defined different levels of autonomy, how a car can be autonomous, right? So level 0 autonomy means the driver is fully responsible and permanently carries out all the aspects of driving. Okay, that is the car that we currently see on our roads. There is no autonomy involved, right? So that is the level 0 they tell. There is no level of autonomy. But slowly they increase the autonomy level. Like if you go to the second or assisted mode, there are two levels available, level 1 and level 2, right? So in level 1, the driver can delegate either steering or acceleration or braking to the system. Okay, so when you think about a self-driving car or a autonomous vehicle, there are mainly three tasks. One is the steering, one is the braking, and one is the steering, braking, and throttle. Okay, throttle or the acceleration. These three things are very important to us, right? So in level 1 autonomy, the driver can delegate either steering or acceleration. So any of the three tasks can be delegated to the system. Other task needs to be done by the driver. So there would be a computer system which would perform one of the tasks and the driver will perform the other two tasks. Okay. So that is the level 1 autonomy. So some form of assistance is given to the driver. That is where the name is advanced driver assistance system. Slowly assistance will be governed and it will be taken to a stage where it will be made completely autonomous, right? So that is the level 1 autonomy. Then level 2 autonomy, the driver must permanently monitor the system. Like you can see, the system will perform several of the driving tasks. It can perform all the driving tasks, but at the same time, it is not like fully capable of doing it. So the driver will keep its eye all the time. Anything can happen. So there would be a steering where the driver would be handling just to see whether everything is going okay or not. If everything is going okay, then he just sit like that, right? If not, then he has to take over and do it, right? So that is where the level 2 autonomy comes. Then level 3 autonomy, which is also known as the automated mode. Why? Because in certain situations, the driver can turn attention away from the road, but must always be ready to take full control again. Like if it's a controlled scenario, then the driver can think like, okay, in this scenario, the vehicle will move without any issues. So he doesn't have to do anything and he can perform some other tasks also. But in case of, let's say, very crowded scenario and all, this software is not up to that level to work efficiently. So in those scenarios, he has to take over. Okay, so that is why it is also known as automated mode. And you will see that most of the companies nowadays, you are seeing these videos and all, are in automated mode or level 3, 4 or 3.5, I would say, where in controlled scenarios, they are able to run it. But if you bring it to actually a very high traffic scenario, it would be very difficult to run. Okay. Then comes level 4 autonomy, which is just an, incremental increment over the level 3 autonomy. The driver can transfer complete control to the system and devote himself to other activities. However, he can take control at any time if he wishes. You see, the difference between level 3 and level 4 autonomy is that it is according to the driver's wish. It's not like he has to, but it is up to his wish. If he feels that this is a scenario which is a very difficult scenario where I feel the software that we have developed is not up to that mark, then he can take over. Okay, so it is that is the very subtle difference that is there between level 3 and level 4 autonomy. That is why you will see that most of the cars are in this range. Okay, where still a steering would be there where the driver would be sitting. Okay, if you see the videos nowadays, you will see that some driver would be there at the driver's seat. But when we are talking about level 5 autonomy, there is no driver at all. There is no concept of driver. Okay, it is like the driver's seat or the seat that is allotted for the drivers will be allotted to a passenger itself. Okay, it is like the complete opposite of whatever we are currently seeing on our roads. Okay, so that is the level of autonomy that we actually need to bring the autonomous vehicles on the road. Okay, till then you will see that all in controlled scenarios and everything can be done. Even you can see there are, like, if you think about level 3 autonomy, you will see that in factory scenarios where you have to transport some goods from one place to the other, then those scenarios in level 3 autonomy can work, because there are not many traffic scenarios that you can encounter there, even not many people you will encounter there. Even if you encounter those people, the kind of softwares that nowadays are there, it is very easy to detect them and bypass them, and then you can move to your original path, right? So in factory kind of scenarios, it is very easy. So that is where this level 3 and 4 autonomy will come. But bringing it actually into a highway environment will take some time. Right? So these are the level 5 autonomy that is defined by the Society of Automated Engineers, and every year they also conduct different kinds of competitions where they call the researchers, where they provide the autonomous vehicle also. What we have to do, we will go with our software, we will we will upload our software there, then they will give a track and there you have to run it. Right? So there they define different autonomies, like whether any car has reached level 4 autonomy or level 5 autonomy, like that. Right? Now coming to the software stack, because as I told you, there is a software involved now, because that software will guide your vehicle and that software will be running in a computer system. Okay, there would be a fully fledged computer system that would be there inside the self-driving car, right? So if you go to this software architecture, there are actually 3 modules that are involved. One is the sensing, then the computing, then the actuation. Right? So sensing component is, that is where all these sensors are being connected and the data are collected. Right? So you see camera, LIDAR, radar, GPS, IMU, ultrasonic sensors, all these sensors can be connected. Even in few cases, multiples of these sensors can be used, like multiple cameras can be used, multiple LIDARs, multiple radars can be used, and all have their own working. Right? So that is the sensing component, and there the most important thing is to connect them in their proper places. That is also very important, and that is also a very good optimization research problem. How to connect different sensors at different places so that you will get the data in such a way that can be processed in a efficient way. Right? So that is also a optimization problem that is there. How to place different sensors at on the autonomous vehicle. Okay, but nowadays when we are doing it, we just follow the previous research papers, how they have connected, or mostly we see, right, whether we are getting the correct data or not. But at the same time, there are patents also on how to place the different sensors on autonomous vehicle. Right? So these are the sensors that are connected, and then once we collect the sensors, then actually comes the computing component. Right? How actually your computer system will process the data. Okay, so there 3 components are involved. One is the perception, planning, and decision, or rather I would say it is like perception, decision, and planning. Right? So that is the sequential way it gives. Perception is the like perceiving the environment. That is the short form known as perception. Perceiving the environment or knowing the environment. Okay. So once we get all the data from all these sensors, how you will perceive the environment. So that is where you will find all these components like localization, detection, and prediction. So what are those? So you see, the detection we already know, right? How to detect different kinds of objects in the environment, right? Then localization means how I will know that the position with respect to others in the environment, right? It is not about just knowing what are the entities. To like as I told you, when I entered into this room, it's not about just knowing who these people are, how they are sitting, and how they are, what is the distance with respect to them, right? So all these things comes into picture. So that is where the mapping and localization comes into picture. Then prediction. Prediction means what are the different trajectories that are followed by different vehicles, what trajectory should the autonomous vehicle would follow, and all those components will come into picture that we are going to discuss in details in future slides. Okay. So in perception, mostly this localization, detection, and prediction comes. Then comes the decision, that is where AI algorithms will come into picture. Once you detect and predict and everything you did, how you will use your intelligence to change the state of the vehicle from one state to the other state such that no critical scenario can happen. Okay. So the vehicle would be in some state. Now once it detects everything and predicts the trajectories and everything, how the vehicle would move from one place to the other, that state change should happen. Right? So that is where the decision component, that is where the autonomous vehicle will take the decision. What should be the go-to path for it so that the critical scenario will not happen in future. Right? Then comes the planning component where mission and motion planning both comes into picture. Mission means, let's say the vehicle wants to move from place A to place B on a map, right? So that is the global mission. It has to follow from A to B. But in between, let's say some obstacle is encountered or something, then it has to deviate from its current path. Then again, once it avoids that obstacle, then again it has to go to its the original designated path. So there is a global planner is there, even the local planner is there, right? In that moment, how to move the vehicle in that vicinity, right? So that is where in mission planning you will find the global planner as well as the local planner coming into picture, right? Then comes the motion planning. Motion planning is the setting of different like kinematics parameters. What would be the velocity of the vehicle? What would be the acceleration of the vehicle that should be set so that the vehicle would move smoothly. Okay. So that is the planning component. Once that is done, like once the decision is taken that the vehicle has to move from this place to let's say place A to place B, avoiding the obstacle and all the motion and mission planning is being done, then comes the actuation component. Okay. So that is where actually the command is sent and the command is executed. Like the vehicle will move in a certain path with this command, right? So that is done by the actuation component, and this is where you will see that mostly this mechanical researchers will come into picture, because all these PID controllers and other MPC controllers and everything that you have heard of, that will be used. Okay. So I generally mostly work in this computing component as a computer science researcher. My area is to like how to perceive and how to do the state change and how to come up with a commands such that the vehicle would move autonomously without creating any critical scenario for the others. Okay. So my research area you will see that mostly lies in this computing component. There is nothing much in the sensing component, because once we get the data we have to process the data. Although I told there are different works like optimization problems, how to place the sensors, that I don't work on. But this actuation component, that generally what we think that the vehicle is already equipped with such a controller, right? Like some drive by wire, we generally call drive by wire, okay, because it is done by the wires connected, right? So drive by wire component would be already there, where we just have to pass our commands which can be executed without any issue. Okay. But if in a sense, if you see the architecture, whole architecture, all three components are being involved: sensing, computing as well as actuation. Okay. So again, actually going into the how AI ML will come into picture in self-driving car, I just wanted to give a gist of how AI ML revolution has happened. So I don't have to go through all of this, because we know AI ML is like used in everywhere nowadays. Okay. Even people use this term interchangeably, AI and ML, which is not, right? I think all are from computer science. So I think all are from computer science only, right? So they know that AI ML are not same. Okay. There are differences. Okay, I will just, there is one slide I will show that, but the whole gist of this slide is that AI ML is like used in everywhere nowadays. Although the research started in the 1950s itself, it started gaining popularity around 2008 with the advent of all these high computing devices and GPU architectures and everything. So after 2008, it becomes like many researchers started using it, and now it is growing exponentially, right? Any research field, if you go, not only computer science, you go to electronics, electrical, mechanical, civil, everywhere you will see that they are using AI and ML. Okay. So the self-driving car is not something different. Okay. As there is so much of availability of data, we have to use some form of ML algorithm to do it faster, right? Now this is the difference that I was talking about AI, ML and deep learning also, right? So AI is like, I would say it's a broader field of research, or in a very simple term, we can just say that anything and everything that can be done by a human being, if you can replicate in a computer, that becomes artificial intelligence. Let's say you want to move from place A to place B, right? So human mind can process it, how to do that. If you can do the same thing with a just simple path learning algorithm, then also it is AI, right? But when it comes to machine learning, you will see that some form of previous data dependency will come into picture. Okay, some data would be involved. I am not talking about the data that we give to the program. That is anyhow there. For any program, computer program that we write, there will be some input, some output coming out of it, right? But when I am talking about data in a machine learning algorithm, it is the previous iteration data should be there. Okay, then only you can predict something for the future. So that is where the machine learning comes into picture. Then again, deep learning is a subfield of machine learning, which is like, of course, the data dependencies should be there because it's a subfield of machine learning, but you will see that the multi-layered neural networks will come into picture. Okay, so that is a concept again. I think most of you must have learned about neural networks and all. So you will see that this multi-layered neural networks will come into picture. Also, the data dependency will be very huge. Okay, it is not in the form of very simple 100 or 200 iterations of data. The data dependency is huge. Again, the question is like, what is huge? There is no limit, right? So it depends upon different kinds of research. For different research, different. So there is like, I can't say that X GB of data is required or this many iterations of the data is required. Okay, there are many many parameters that comes into picture to choose what data could be enough for the deep learning algorithm that we are going to run. So you see this self-driving car is it is connected with different sensors. So data is huge, right? Okay. So maybe I can stand here. Okay. So the data is very huge, right? Even the previous iteration of data is existing, because you will see that there are many data sets in this area where they have come up with labeling of what is required, right? So data is also there. So you will see that in most of the algorithm that we are going to discuss in this autonomous vehicles, they generally use this machine learning and deep learning algorithms, and mostly this deep learning algorithms and convolutional neural network algorithms will come into picture. Okay, so this slide again, this AI ML is being used everywhere. Okay, whether it's healthcare or accounting, cyber security, anywhere, robotics, everywhere it is being nowadays used. So the self-driving car is not something like different. Okay, because there is so much of data availability is there, and we have to process them faster. Okay, so that is why AI ML, ML and deep learning algorithm will come into picture. Okay, so these are the working of different sensors. Like if you think about a camera, okay, if you think about a camera, generally you will see that the camera is used to find out like objects that are in the near vicinity, right? What is the what kind of different objects like pedestrians or bicyclists or the cars or trucks and vans, what kind of objects are there? Then you will see that this camera sensor has a like you can only detect in the 2D plane. Right? If those who know about image processing, they would know that in case of camera, we just get the 2D data. We don't get the actual depth. And when it comes to a self-driving car, we actually need the 3D, right? Everything is in 3D. So we need some sensors that would overcome the drawback of this camera sensor, right? So that is where you will see, I find that this LiDAR sensor are being used, where we get the data in 3D. Again, the LiDAR sensor has its own drawbacks. So that is why you will see that the most preferred method to do the perception in a self-driving car is to fuse the data, right? LiDAR plus camera fusion, or there are other sensors like this radar sensor, which is also in a 3D sensor, but it gives the velocity information accurately. Okay, so if you find the velocity from other sensors like LiDAR and camera, those are not accurate. But when you use a radar sensor, you will get a very high accurate velocity. So it is generally what we do, we fuse all three sensors, LiDAR, camera and radar. Again, the complexity becomes more, but the accuracy of information is much higher, right? So all these things that we are going to discuss in future slides. Okay, so this slide I can skip. Okay, so this is what I was talking about perception, where the car senses the environment around it, and different sensors that are connected. Already discussed about this, right? So when it comes to camera, you will see that the different tasks that we can do is that 2D object detection. You see, whenever it comes to camera, I am writing just 2D, because as I told you, the depth information is missing. Okay, even if you take a photo in some scene, right, as a human being, we can know that what is the distance. Why? Because from our childhood till now, we are trained in such a way that we know the depth, right? Because we have binocular vision available to us, two eyes are available to us, so we know that what is the depth and all, right? So we are trained like that. Even if we close our one eye, we can say what is the distance, right? But when it comes to a camera, if you take a photo, you will never know that, right? Or you think about a computer system which has not seen it previously, it will not know the depth. So generally, when we do any kind of perception task with the camera, we say that it's on 2D plane only. It's not on 3D plane. So actual depth would be missing. So this 2D object detection, semantic segmentation, traffic light detection, lane following, all these tasks are done using the camera sensors. I will discuss them. Then using LiDAR, when it comes to LiDAR, you will find that 3D will come into picture, because the data would be in 3D. Along with your X and Y, there would be some other axis called Z, where you will get some other form of data. Okay, 3-dimensional data we are going to get. So all the tasks that we did with camera can be replicated with LiDAR to some extent, but in 3D. But you will see that we will not cover all the tasks that are there in camera, because those are not required. Only the tasks where camera fails miserably, that is where the LiDAR will come into picture. Okay. Then comes the radar, where we will get the velocity and range estimates. Then another sensor is used, that is known as the GPS, or the Global Positioning System, or GNSS system, where we put the vehicle in the global perspective, right? So we will know that where the vehicle is with respect to the global map. How that helps? It helps in a way that you can find out other vehicles in the environment using their GPS. Okay, if the vehicle to vehicle communication is there, or there is some form of central server is there where everyone is sharing their GPS location, then you will find the location of other vehicles in your environment, right? So that is also helps in some way to find out this blind spots and all. Okay, so in form of AI and computer vision, we generally do not use this GPS. This is just for a global mapping perspective, the GPS is used. Then IMU is also there, where this inertial measurement unit to find the acceleration and gyroscope measurements, right? What is the acceleration and gyroscope of the autonomous vehicle as well as the other vehicles in the environment. Okay, and the most important research area in this is the multi-sensor fusion. How you can fuse different sensor data. Right, camera plus LiDAR vision, LiDAR plus radar, camera plus LiDAR plus radar, all this fusion, how it can be done. Okay. So this is how a typical self-driving car sensors are being connected, and you will see that this camera is generally connected at a place where we can see the front view. Okay, here in this diagram you can see camera is connected at the top, because in this diagram there are multiple cameras that are used, and that covers the whole 360 degrees. Okay, only one, if you want to use a 360 degree camera, it might not work, because in 360 degree cameras you get this fisheye view. Okay, it will not look like the way that we see the environment. So you have to use rectilinear cameras, where it will give you the way that we generally perceive the environment, right? Rectilinear views that to have a overlapping field of view, right? So that you can cover the 360 degree. That is one way of doing it, and some other researchers, they generally just connect a camera just at the front, okay, so that they can just see the front. Okay, when I say they just see, it's about the computer system. The computer system can see just the front, and with other sensors like this LiDAR unit, you see it is also placed at the top, right? Because LiDAR is a 360 degree sensor. Okay, then it will give you 360 degree data. Okay, so it has to be connected at the top. Okay, so LiDAR, we will see that always it will be connected at the top. And camera generally it is connected at a place where it can see the front. Okay, when it is required that 360 degree needs to be covered, then it is 6 or multiple cameras can be connected at the top with overlapping field of view. But radar sensor, you will see that they are connected to the side to know the velocity of different vehicles that are coming in the near vicinity of the vehicle, right? And there would be you see, apart from the sensors connected, even there is a additional LiDAR unit. You can see that is just a very low cost LiDAR that we generally connect at the down, okay, to know different kinds of potholes and the speed breakers. Okay, so there are generally 2D sensors. Okay, these LiDARs, there are two types of LiDAR comes. One are the 3D LiDARs, which are very high costly. The minimum cost you will see that 6-7 lakhs, and these 2D LiDARs which are low costly, which where we can use on the like to know this pothole and all those things, right? So that is why you will see that these LiDARs are connected at the bottom. Apart from all this, you will see that there is a main computer in the trunk. Actually, a computer system would be there where all this data would be saved, and there all the computer vision and machine learning algorithms would be running. Okay, from there the decision would be taken what kind of commands should be executed such that the vehicle will move autonomously without affecting the others, right? So that is where the main computer system is there in the trunk. Okay, so this kind of already discussed. This is just a overview of what are the tasks that can be done. So if it comes to image processing, you will see that all this traffic light detection, lane flow detection, object detection can be done. It comes to LiDAR, then 3D object detection can be done. Then using radar, we can again do the radar processing to do the radar object tracking and finding the velocity. But most important thing is the fusion part, where once you fuse all this data, this camera, lidar and radar data, there you find the actual, what do you say, refined outputs. What kind of objects are there, and what is the distance, what is the velocity, and even what is the track of those vehicles and all those things, right? So these are the two important things. One is the how to detect all the traffic lights, the posts and everything. Then apart from that, what are the different objects that are there in the environment, what are their actual geometries, what kind of velocity and, or I would say what kind of kinematic profiles that the other vehicles that they have in the environment, and apart from that, what distance they are there with respect to the vehicle. Apart from the distance, and even the angle is important, at what angle they are moving, okay. So all these things are done using this kind of sensors, okay. Now we will discuss one research area in all these sensors, like, so as I told you, this 2D object detection is there, okay. Nowadays I think this 2D object detection is very common. You must have heard about this paper YOLO. Have you heard of this term? You only look once, and every year you will see that a new version is coming, with a new better version is coming, okay. So what is 2D object detection? It reads the image data from the camera and provides image based object detection. That is very important. On the image, what are the different objects that are there with their bounding boxes. When I say bounding boxes means there would be some area that they are confined to on the image, like let's say on this scene I take a photo, then all the people that are there in the environment, they should be shown, saying that these are the persons and this is the area that is confined to, okay. So that is the 2D object detection. Now you take this scenario to a highway environment, what kind of objects we can get? We can get different kinds of cars, vans, trucks, okay, or pedestrians, bicyclists also can come, okay. So those objects should be localized, and at the same time what kind of objects it should tell, right. So that is why 2D object detection, you will see that is a very interesting problem, where you do classification as well as regression. Classification means you find out what kind of object it is, right. So that is where you classify whether it belongs to a car, whether it belongs to a van or truck or bicyclist or pedestrians, like that. That is one problem. The other problem is the regression problem, where you try to find out what is the bounding box, okay. It is not just finding where what kind of object it is, you need to find out what is its xy coordinate and the what do you say, when you say a bounding box, there should be some top left corner and top down right corner, right. So you need to actually know those values x1, y1 and x2, y2, then only you can draw the bounding box, right. So it is a classification and regression problem. So when you will go to the research articles based on this 2D object detection, you will see that this convolutional neural network architectures are being used. If you go to actually 2014 back, right, before 2014, you will see that this for this 2D object detection, generally they used a approach called as selective search. So what they used to do is that is not based on convolutional neural network. They just finding out that what in the they used to do is that they used to find out some proposal boxes just covering some of the areas, okay. So you can see some of the research papers based on selective search. Those are not convolutional neural network based. But after 2014 onwards, this have you heard this term RCNN? Okay, so that is the first paper that actually came into picture for this object detections based on convolutional neural networks. Okay, so that is where they actually use the selective search approach in a neural network way. How the same thing can be done in a neural network? Then they started doing it autonomously with this. They started doing it with this deep learning based approaches. Okay, and that is where, based on this RCNN approach, this YOLO architecture came into picture. Okay, where they completely removed that selective search based method and completely came with a end-to-end approach, where you just pass an image and you get the output where the different objects are and what are those objects. Okay, so I will not go into the article about YOLO and all that. Those things are nowadays readily available. You can just go through it, but you can just see why 2D object detection is very important from autonomous vehicles perspective, because there are so many objects and there is a camera that is available to us, and we need to know what kind of objects and where they are on the image plane. Okay, but again the biggest problem is just by knowing where they are on the image plane is not going to help, because the distance needs to be known. What is the distance with respect to the vehicle? That needs to be known, and that problem is not solved by 2D object detection. Okay, that we will see how it can be overcome using different other sensors, right? Any questions? Right. So then 2D semantic segmentation. Again, I am writing 2D because we are still in the camera data only, right? So semantic segmentation is the pixel wise classification is done on the whole image. Like let's say you get the image data from a, you just imagine the car is moving in a traffic environment. So you get the front portion of the view, right? Front portion view. So there you will see that the road is there, the different cars are there, right? So this 2D object detection, it will find different objects, right? But it will not tell where the vehicles, or we can see these empty spaces, right? So if you want to know that, then what you can do, all these cars can be given a different color, all the roads can be given a different color, even the skies pixels can be given a different color, building pixels can be given a different color, right? So pixel wise we will give a class. Okay, so this semantic segmentation, although is a regression problem where you try to find out what is the corresponding value corresponding to a different pixel, it is a combination of classification because every pixel is classified. What is the class of a single pixel? Understood? So if there is the whole image is there, we will find for all the pixels in the image what is the class they correspond to. So some class pixels should correspond to the car, some pixels should correspond to the road, some pixels should correspond to the sky. So every class will be given a different color. How does that help? That helps in finding the free space. Let's say you know the space or know the pixels where the road is there, then you can say that okay, this is the path that can be empty, right? So and the vehicle can move in that path. Although not in 3D, you will not get in 3D because it's a 2D 2D view that you are getting. But at the same time, you will get some kind of information that there is the road. Right? So the vehicle can take some turn from that direction, right? So that is where the semantic segmentation is very much helpful, and you will see that here also different kinds of convolution neural network approaches are being used. Okay. Okay, so this is just a visual representation of how this YOLO algorithm works. Okay, I will not go into details because these are readily available nowadays. So it is just like you see. The input image is there and it will find out the bounding box corresponding to different kind of objects. Like in this case, you see there are three objects. This dog is there, this bicycle is there, and there is a car. So at the end, once you run through this YOLO algorithm, you will find the bounding box corresponding to different objects that are there in the environment. Okay, if you actually go to a highway environment, so you see. So these kind of different objects that are there. So it will say what kind of objects as well as what is the bounding box. Now here you can see, knowingly I put this image because you see there is a car but still it is not able to detect it. There is a motorcycle, still it is not able to detect it. Okay, so it's not like this YOLO architectures are like foolproof. Okay, so when it comes to low visual environment like in this case, right, so they don't work that very well. Okay, so the visual and the lighting and everything should be perfect to work for this YOLO kind of architectures, right? So that is where the research is also there. Okay, because everywhere on a highway environment there is no guarantee that you are going to get very light environment, right? Even the autonomous vehicles should work very well in night kind of scenarios, right? So that is where the research is still there. It's not like YOLO architectures are there and object detection is very accurate and that should directly work in a self-driving car environment, right? So the research is there where in this kind of scenarios or night scenarios, how we will detect different objects in camera plane, right? So this is the semantic segmentation that I was talking about. You see, all the classes are given a different color. Like all the cars you see, they are given a red color. All the road pixels, they are given a different color. All the buildings are given a different color. The sky pixels are given a different color. So by doing that, we are able to semantically segment the whole image. We are knowing where the different kinds of objects are, right? So if you go for 2D object detection, it will not detect the road, right? It will just detect different kind of objects that are there. But here you see every pixel is given a different class, where it was not happening in case of 2D object detection. In case of 2D object detection, only the objects are being detected, right? Then comes the traffic light detection, which is also a very important task in case of vehicles, because you need kind of traffic color is there, whether it's green or red or orange or yellow, whatever. So first thing first, to know whether a traffic post is there. Once you know what kind of traffic post is there, you need to know what is the current state of the traffic, right? So that is also a very good research area where we need to find out what kind of traffics are there. Okay, there are different data sets in this field. We can search on that. And again you will see that all these convolutional neural network approaches are being used to classify these images. Okay, so when you get an image, you need to find out whether there is any traffic light or is there or not. If any traffic light is there, then what is the current state of the traffic light. Okay, so that can also be done. Then lane following, generally you will see that this lane following works in controlled environment. When you go to a controlled environment where the lane markings would be there, how the vehicle would move on that lane markings. Okay, here again mostly I had come up with one approach where we generally don't use the convolutional neural network approach, because our first point should be, can we come up with a very simple algorithm which would work very fast. Okay, so if you go to deep learning and convolutional neural networks, it is very heavy because you need so much of data, then we need the neural network architectures and all, right. This kind of work, right, where you have to follow a lane, which is a very trivial problem in robotics, right. In our BTech also we would have tried something like lane following of different kind of robots, right. So if you want to do that in a controlled environment for robotics, you can search on one research area called as vanishing point. Okay, so vanishing point is like a point where the parallel lines intersect, okay, or parallel lines meet. Okay, the obvious question would be the parallel lines don't meet. Okay, but if you see in a, let's say you are a very you are standing in a in a highway where there is nothing on the front, it's just in a desert environment, you will see that these lines would look like they are meeting. Even though they are not meeting, it will look like they are meeting at some infinity point. Okay, so that is known as the infinity point or the vanishing point. And if we try to keep that infinity point at the middle of the image, then the vehicle would move on exactly on the middle of the road. Okay, so that is the very simple concept that we generally use for lane following of self-driving cars. Again, when it comes to actual where all these traffics would be there, then it is very difficult because other objects will come on the lane markings and all. But in a controlled environment where you know that there are not many obstacles that can come, this kind of works very good. Where just by looking into the vanishing point, the car can move following the lane. Okay, just that you have to get the image out of the front camera and process it to find out the vanishing point. Okay. Then apart from that, 2D tracking is also there. Okay, so the difference between detection and tracking is that in case of detection, you just find out different kinds of objects, but tracking gives a unique ID. Okay, if you ask me, you see in this room I just know two persons. One is the Subhankar sir and Rucha madam. Okay, apart from that I don't know anyone. Rucha madam, right? I don't know, I just saw your profile. But apart from that, others are like just persons to me. I can't give a unique ID to you. Okay, so it is like a detection, just persons. But if I know your name, it becomes tracking. Because I know I can give you a unique ID to you, like person X, person Y, person Z, like that. Understood? So that is how in case of self-driving car, detection is just finding the objects, tracking is like giving a unique ID to them. How does that help? If you give a unique ID, you can know what track they are following. Understood? So I can say that, okay, ID 1 or the car 1 is moving in this path, car 2 is moving in this path, car 3 is moving in this path. Right? So that is where you get the trajectory prediction for different vehicles in the environment. If you can do the trajectory prediction for different vehicles, the autonomous vehicle can come up with or optimize its path. Right? So that is where the object tracking is very much important. But again, this is an 2D object tracking because it is done on the camera plane. Okay, when it comes to camera plane, it is just on 2D, and that is not going to help that much from the autonomous vehicles perspective. Okay, so if you want to actually do it, then we have to do it in 3D, and that is where you will see that the other sensor or the most important sensor in a self-driving car, LiDAR, will come into picture. Okay, this is the most important, I would say, the sensor in case of self-driving car. Why, I will tell. First, we will look into the working of LiDAR. How does it work? It sends out, so the short form, the LiDAR is the short form for light detection and ranging. What it does, it sends out very short light pulses at different angles across the field of view and receives the photons reflected back from an object. So what it does is that there would be, if you look into the LiDAR, you will see that it is cylindrical. Okay, so there it sends the laser sensor, laser pulses. Okay, and the laser pulses go, hit, and then come back. Okay, so you know the velocity of light, right? So the velocity of light apart from the time it takes to go and come back. Using that, it actually finds the accurate distance to some point. Okay. But you will see that what happens is that the laser sensor would move in a vertical plane, okay, from top to down, okay, covering the 360 degree. Let's say from some minus 20 degree to plus 20 degree, it will move, then it will go hit and come back. That too at short pulses. It's not like very continuous. So the data that we are going to get is just points, because you see at short pulses it will go hit and come back, go hit and come back, right? So at short pulses you will just get some points around the environment. So the data that you are going to get out of a lidar is a point cloud, okay? That also you can search this point cloud environment we tell, okay? So we will not get like in case of a camera we get a very smooth image, right? Everything is continuous, every pixel has some intensity. But in case of lidar you will see that there would be so many sparse things, right? Only you will get the points where some object is there. Like in this environment, if I place a lidar, you will see that you will get the points where different persons are sitting. You will get the points where these walls are there. Apart from that, everything will be sparse, right? So you will get a point cloud environment of this environment. Now we have to process those point cloud to know what kind of objects are there and their 3D structure. So when I say 3D structure, means we need to know about what is the dimension of different objects that are there in the environment, what is the distance that from the autonomous vehicles, and at the same time at what angle they are with respect to the autonomous vehicle. So all these things need to be known, right? So this is the lidar, and these lidars are very costly. Even the like in case of camera we tell them like this is a 5 megapixel camera, 10 megapixel camera to know the resolution. Similarly, in case of lidar, the resolution is known in terms of like scan lines. How many scan lines it will do in the vertical plane. Okay, then it moves from some minus 20 to plus 20 degree. That is generally this sensor, this Velodyne sensor is there, Velodyne lidar is there. That is done from minus 20 to plus 20 degree. So we say that how many scan lines it takes. Scan line means this rotational planes. Okay, how many rotational planes it moves, right? So based on that, see, this is what we are saying. So you see the autonomous vehicle generally will be at the middle, and the lidar sensor, as I told, will be placed of the vehicle. Okay, so that is why you see near vicinity of the autonomous vehicle there is no lidar data, because the near vicinity it would not be able to cover. It's like if you place a sensor on the top of the vehicle, then near vicinity will not come, right? So that is why the first concentric circle that comes after some distance, and then it can cover up to 100 meters. Okay, so you see as it goes away from the autonomous vehicle, the distance between the concentric circles becomes more. Okay, so this is where the resolution is defined. If you get more concentric circles, then the resolution of that lidar is very high and it is very costly. Even there are lidars which cost up to 30-40 lakhs, right? So this is a 64 scan line lidar taken from one data set. Okay, that lidar costs around 30 lakhs. But this one lidar sensor that I have brought from one of my projects is a 16 scan line lidar, which costed me around 5 lakhs. That too around 2-3 years back. So I don't know now, currently I think it's 6 or 7 lakhs or something. Okay, so these lidars are very costly, but at the same time very accurate sensors. Okay, they will give you accurate depth information. So the most important task that can be done using the lidar sensor is the 3D object detection, which is like an extension to 2D object detection, but at the same time depth would be there. Okay, so in case of 2D, as I told you, you know what kind of object it is and what are the different this bounding box, right? But in case of 3D object detection, you get much more information, like you get what kind of object it is, that is the classification task. But in regression, you get the bounding box in 3D. Okay, so there you are just getting 4 points, here you have to get, you think about a cube, 8 points, right? So 8 points you have to get. But at the same time, you need to know what is the angle that the object is with respect to the autonomous vehicle. So that angle is also very important. And what is the distance of that object with respect to the vehicle. So there are many more information that you get in case of a 3D object detection. But at the same time, processing this kind of data is also very heavy, because you think previously you just have a camera image which is very continuous and some resolution was there, right? But here you have a 3D environment, right? That too up to 100 meters. So much of point cloud comes in, sometimes in millions comes in one go you will get millions of point clouds. Right? Now how to process that millions of point cloud data? to get accurate information out of it. So this kind of convolutional neural networks or the deep learning architecture that we are going to use in this are very complex. Okay, and they, even if you go to this YOLO architecture, you will see that they work in real time. It works up to 30 frames per second and even up to 45 frames per second if you use a very good GPU, right? But this LiDAR, even if you use a very good GPU, it can go up to 10 frames per second or 12 frames per second. Okay, so the actual research here lies in coming up with a very lightweight architecture that can process this heavy data. Okay, because the data wise we can't reduce it. That is the data that we need. But at the same time, can we come up with a very lightweight neural network or computer vision convolutional neural network architecture that can process it very efficiently, giving the real time efficient outputs. Okay. So knowingly I am not going through the different architectures that are there because that will take too much of time. Okay, so maybe in future I can give those talks, but in gist we can know different kind of research areas that can come out of this self-driving car technology. Okay, so this is what I was talking about, 3D object detection. You see, from LiDAR point cloud data we get the 3D bounding boxes. Okay, apart from what kind of object it is, we get the 3D bounding boxes that are there in the environment. Okay, this is just a one visualization tool that I have used. Okay, when it comes to robotics, generally we use this robot operating system. Okay, have you heard this term? Anyone? Robot operating system. Okay, so generally for robotics environment we use the robot operating system where there is a visualization tool called as RViz. Okay, so in RViz generally all this LiDAR data, camera data, everything we can import to it and we can visualize while we are taking the data. Okay, so even there is a way by which we can collect all this data in an environment and run it in our system as if we are doing in real time. Okay, so those are known as ROS-baked files. Okay, so that is also a very good concept. Those who are working in this robotics and all, they can work on it. Then apart from 3D object detection, we can do also localization. Because now we are in 3D and we know what kind of objects are there and their distance and all, we can definitely do some kind of localization and mapping. Okay, generally we do this simultaneous localization and mapping to create the SLAM environment. Okay, so that we can know the whole map and all those things. Okay, so that is where the localization comes into picture. So I will not go into details, it's already too much of time. Okay. Then comes the radar sensor, which is again a very, as I told you, this LiDAR sensor is very high costly, right? But when it comes to radar, radar is very efficient with low cost and small footprint. Okay, it is capable to determine targets at long range with accurate velocity. That is the most important thing. That is where you find the accurate velocities. So it is not about just finding the where the object is. At the same time, we should know their kinematics parameters, right? Velocity and acceleration and everything. Okay, so that is where the radar comes into picture, and you will see that at some point of time we have to do the fusion between radar and LiDAR, because LiDAR will give you what kind of object it is and radar will tell you what kind of velocity of those objects. Okay, so we can come up with a very good accurate environment where LiDAR, camera and radar can be used. But the problem is that again it is like its sensitivity in dark and poor weather conditions also helps to cover domains where LiDAR or camera may fail. Okay, so it works in different kinds of poor weather conditions also where the camera and LiDAR will not work. Working transmit electronic waves and transmits electromagnetic waves and receives reflected waves. So if you go to the working, the difference is that here electromagnetic waves are used. In case of LiDAR, these laser beams are being used. Okay, so the pros are operates in bad weather conditions, low cost and accurate velocity detection, but the con is that lower resolution. Okay, it is the lower resolution with respect to the LiDAR. Okay, so both sensors can be used. So GPS nowadays this lightning is very frightening. Okay, GPS and GNS. So if you come to these two sensors, right, this GPS and IMU that we know, GPS gives you the global positioning system where the vehicle is with respect to others in the environment. There is no as such what you say this AI and ML or computer vision is being used. It is just how to process the data to come up with an accurate global map. Okay, even if you think about AI, we can use it because this path planning, if you think, even though it is not using machine learning and computer vision, just a pure vanilla path planning algorithm, if you come up with, then it is just like a AI algorithm only. Okay, so AI can be used to map the environment in this whole global point of view, but at the same time there is no convolutional neural network or deep learning architectures that are being used by this GPS and IMU data. Okay, so IMU is just the inertial measurement unit, where what is the velocity and acceleration of the vehicle, as well as not the velocity, mostly it gives the acceleration, but at the same time we can get the velocity out of acceleration. But gyroscope also, like what is the heading of the vehicle with respect to its own frame of reference. If we know that, then we can also find out the gyroscope of other vehicles in the environment, because we have the 3D object detection, we know what is the angle of the vehicles with respect to the vehicle, right, with respect to the autonomous vehicle that we are driving, then we can find the gyroscope and acceleration information of other vehicles also. Okay. Then comes the multi-sensor fusion, which is again a very difficult task. It will take so much of time. I have not put much of it, but it's like, you see, every sensor has some limitations. Like you saw that in camera we don't get the 3D, but in case of LiDAR we get the 3D, but it is a very high processing sensor. At the same time the data is sparse, it doesn't give you like continuous data, right. So again the drawback of LiDAR, as I told you, drawback of radar is also there, because radar is very low resolution. Although it can give you velocity, it can give you low resolution. Again, in different conditions, different sensors work. Like if you say not work, right? In LiDAR might not work, but radar can work. So it's all about how you use all these sensors, fuse that data and use it in different convolutional neural networks or deep learning algorithm, such that you come up with a better accurate information. So that is where a most important research area comes, is the multi-sensor fusion. Okay, where we design different kinds of deep learning algorithms which will just not take one mode of data, but multiple modes of data. Multimodality data can be processed through the neural network, and there it will select what kind of data it should use. Okay, it is not just like all these three data will be used. The neural network itself will decide what is the fusion that it should use, whether it should go for camera radar or whether it should go for LiDAR radar. So that kind of modality it should choose. Okay, and based on that it will take the decision what command should be done. So it should be end to end. Data would be passed, but at the end it should say what kind of decision should be taken, right. So that end to end neural network we can design based on multi-sensor fusion. Okay, again there you will find that there is another optimization criteria is required, external calibration. Because you see, when there is only one sensor, you just have to do the calibration of that sensor. But when there are multiple sensors are there, right, and they are placed at different places on the autonomous vehicle. Okay, at different places of the autonomous vehicle you are placing those sensors. Now the question is how to do the how to transform the frame of references. Because with respect to the LiDAR, the object it is placed, let's say it is at position X, but with respect to the camera it would be at Y, right, and we need to know how we can do the transformation between them, or we need to transform it to some other frames of references which is common for all, which we call as the vehicle frame of reference. So that is where this external calibration, to know where the object is with respect to both the sensors, so that they can be transformed to a common frame of reference. Okay, so that, believe me, this is although the external calibration we have heard of it, but it's a very difficult field, because you have to optimize so many parameters, then you will find out that transformation matrix. Okay, and this external calibration is different for different vehicles. Okay, even though if you change the position of the sensor little bit, the calibration changes, and you have to do that engineering problem again and again. Okay, generally what we do, we place a cardboard in front of the vehicle, then we try to find out where the different cardboard boxes are there, right. So where those are with respect to the LiDAR as well as the camera as well as the radar, then we get so many points, right. Then we come up with some optimization which will satisfy all these points. Okay, more the points, better is the optimization. Okay, sometimes there is some limit. It's not like always more points will give you the more optimized way. Right? So that is again a engineering problem, but at the same time a difficult problem also. Okay. Apart from that, you will see that different sensors will follow different coordinate axes. Like camera, generally X is towards the right, Y is down. Okay, Z is suppressed, but Z is towards the front. But when it comes to LiDAR, that value that we are using, X is towards the front, Y is towards the left, and Z is towards the down. Okay, so every sensor will have their own coordinate axis. The question that you could ask, why they are following like that, it depends upon the vendor. they are following that, so we have to live with that, right? So that is what, so that problem is also there in external calibration. So this is one image that I have taken from a very famous dataset, Kitty dataset. Okay, that is the self-driving car dataset that researchers generally use when they start working on self-driving cars. Okay, apart from that, there are other datasets also. So this is the camera lidar fusion, where you see where we have fused the data so that you can see even when there is some space, it is also visible with the lidar. Because if there is no space, then there would be some point cloud would be visible over here, right? Now that we have fused the data, you can see that even in the lidar plane, when I say lidar plane means these points, okay, there also we are getting some space. But when there is some building, it is able to detect some point cloud is there. Okay, so that means we have fused the data between camera and lidar. Okay, so I think it will go on. Okay. Then similar to 2D object tracking, 3D object tracking can be done, right? Giving a unique ID to all these vehicles or objects that are there in the environment, right? So that is where mostly we use this Kalman filter and different versions of Kalman filter are being used, where we get the data from different iterations and come up with like where the vehicle would be and all, right? So that is where we do the 3D multi-object tracking. Again, I will not go into. Again, the most important thing is that unique ID will be given to each of the vehicles. Okay, some unique ID will be given. Some from those unique IDs we can get 3D tracks. This is more important because in case of camera we are just getting 2D tracks which was not in 3D, so that was not very much important. But in case of 3D tracks, we will actually get the trajectory. In 3D, what is their trajectory? So we can predict what is their trajectory in future, and based on that, we can come up with a optimization criteria which could help the autonomous vehicle to find out its own trajectory. What trajectory should it follow such that it will not hinder the path of other vehicles, or the vehicle should not hinder its path, right? So that is where this trajectory information is very much important, which can be done from this 3D multi-object tracking. Okay. So then lidar radar fusion can also be done, because you see when you have the velocity information, you can get the distance information, right? Integrating it will give you the distance information, right? Velocity integrated, it will give you distance. And lidar also is giving you the distance information, because depth information you are finding. Now you have two sources of information which gives you distance, right? So then you can use some filtering mechanism to come up with a better estimate, because as I told you, in some of the environments lidar might not work, in some of the environments camera might not work. So it's better to come up with some mechanism which would fuse both the data and come up with a better estimate, right? So those environments where lidar is not there, the direct radar data can be used. Those environments where radar is not working, direct lidar can be used. Or if both are available, then fuse the data, then come up with a better estimate. Okay, so that is where again you will see that all these Kalman filter mechanisms, extended Kalman filter mostly is being used. Okay. If you go to the data set, then as I told you, Kitty is the first point in autonomous vehicles. Every researchers, those who start in this area, generally work with the Kitty data sets. Even Kitty has a extended version now, Kitty 360. Okay, so that also we should use. But apart from that, other data sets like NoSys, Waymo, Argoverse, and many data sets are there nowadays. Okay. But if you come to the Indian scenarios, generally this IDD data set by IIT Hyderabad, that is the first data set that was published, and they had taken all these images and everything from Bengaluru and Hyderabad. Okay. The biggest difference that you will find is that the convolutional neural net architectures or the deep learning architectures that I discussed, mostly they are trained on the data sets from foreign scenarios. So if you bring directly those kind of architectures and their pre-trained weights and come to Indian environments, it is not working. Okay. For a very simple example is that auto. You will not get in foreign scenarios. So if you come and run in our Indian scenarios, these autos will not be detected. Even the buses are not detected, because the structure of buses changes, right? Even to some extent this bicycles and everything. Okay, so what we have to do, we have to collect the data, then train in our own setup, right? Then we will be able to detect them, right? So that is where the transfer learning and everything are used. But if you use this IDD data set, you will see that mostly these Indian scenarios they have covered. But the problem is that you will see that all are camera images. Till date, there is no data set based on lidar in Indian data in scenarios. Okay. Currently, this IIT Hyderabad, they are working on it. You have heard about this Technology Innovation Hub IIT Hyderabad, IHAN, right? They are coming up with a data set, and I heard that I have a project with them, so that is where they told me that they are coming up with some LiDAR data set now. LiDAR, camera, radar and everything there. So it is still under process, still it has not come. Different challenges are there, as I told you, although this 2D object detection is a very, burnout field where many researchers have worked, but when it actually comes to the self-driving car environment, it is difficult. Because all lighting environment, different kind of scenarios that you are going to get, and all the objects that are there is not covered in the foreign data set. So research is still there, even in 2D object detection. But apart from that, this 3D object detection tracking is the most important research field nowadays. If you go to the CVPR, ICCV, ECCV, you will see that every year 4-5 papers are coming in. So it is like currently the hot topic in autonomous vehicles. So those who want to work on this field, I would say this is the field. 3D object detection and the tracking is the most important field. Even one of my PhD scholars is currently working on it. Then lane following, LiDAR and image segmentation, traffic light detection. Again, localization is a very important. It is always important. Okay, localization, the simultaneous localization and mapping, or even parallel tracking and mapping. This is always a green field in robotics. Okay, because the environment never remains same. Environment is always different, right? So when environment is different, the simultaneous localization mapping method is different, right? So if you go to a highway in scenario, it is different. If you come inside a room, it is different. If you go to some different terrain, the approach would be different, right? So that is why localization is always a green field of research in this kind of these areas, right? So LiDAR data we are receiving in through the RVs, camera data we are receiving through the RVs, okay? So what I did, using the LiDAR data, this 3D object detection done using one algorithm, okay, that we had developed. 3D object detection done. Again, those box arrays are created and passed. Then we didn't do any 2D object detection, but what we did, using the external calibration, as I told, no transformation can be done. Using this external calibration, this 3D bounding boxes are converted to its corresponding 2D. Okay, it is just shown in 3D, because in camera we can't see in 3D. It is just a slanted box is just being shown. But what is done, we didn't do any 2D object detection over here. Just that 3D object detection, we just we just transformed into a different plane using that external calibration matrix, right? This is one point. And other point is that here we are doing the localization thing. You see, every object is given a track. Like there is some vehicle that is moving on the front, we given a track of 2. There is some other object that is given 34. So every object is given a different unique ID. And based on those unique IDs, we are able to find the tracks, what tracks that they are following. Okay, so you see, this is the vehicle. We generally call the vehicle as ego vehicle and other vehicles as the target vehicles. So that is what we are able to plot it. And this position X and position Y we have taken from the GPS location of the vehicle. Okay, so this is like, we can say that this is the global north and this is the global east. Not with respect to this one, but this road is in such a way that it is in the 45 degree to the global north and global east, because we have taken the GPS coordinates and we have tried to plot it. Okay, and again the other vehicles GPS coordinates were not available to us. So what we did, using this 3D object detection, we found out what is the distance, what is the angle and all. Then using this earth radius, okay, there is an approximation method. Okay, using that earth radius and everything we use, it is known as some Heron approach or something. Using that, we found out what would be the GPS coordinates of other vehicles in the environment. Okay, so then we tried to plot it. Okay, so that is where the localization is happening. This is just one video I thought I will show. Okay. So these are the things that we discussed. Okay, different kinds of sensors and what are their workings and what are the research areas that could come out of it. Okay, knowingly I didn't different neural network architectures, because that will take too much of time to go into. Maybe in future, if I get time, then I can go through this 3D object detection and tracking in detail, because that is where mostly I focus in my research. Okay, yeah. So yeah. Thank you for being present.